My name is Dana Golden. Today we're going to talk about tree models. So tree models are basically, think about it as instead of running a linear regression where you have kind of continuous relationship, in tree models you kind of have a break. So this is a lot like adding a bunch of dummies to a linear regression, only the dummies are found automatically. So we begin by loading the iris dataset, and then we're going to do a train test split. We're going to create a decision tree classifier, and we're going to train it. So we have trained our decision tree classifier from sklearn. We're going to predict using the decision tree. We're going to get a confusion matrix. So if precision is 1, recall is 1, F-score is 1, accuracy is 1. This is a very small data set, so there's not tons of variation, which is why we have these perfect prediction. But notice kind of the idea of the tree is you have certain characteristics. You have petal length less than 2.45, and then you have, that classifies things perfectly. You have petal width less than or equal to 1.75, then petal width less than 4.95, and then you do petal width less than 1.6, and then you get versicolor, Virginica. So it's classifying the purples at the end are Virginica, and then it's telling in the intermediate, it's telling you the most common class. It's telling you the Ginning index, which is a measure of entropy, how much distinction there is between the values. This is kind of overfit. Let's try to train a decision tree classifier. I'm forgetting the command here, so Python is sklearn. So we go here, decision tree classifier, and then max depth. I want max depth to just be equal to 2. So this is going to make it worse, but this is going to lead to less overfitting. So you see here how we have all these characteristics we're fitting on, probably fine for this data set, but in a lot of data sets that would lead to problems on test. So this isn't really decreasing overfitting because overfitting is about the test data set, and we're fitting the test data set pretty well regardless. But on more out-of-sample data, we might not. So here is that model with a little bit less max depth. We're not classifying everything perfectly, but we are classifying things pretty well. We've got 3 good classes. We perfectly classified the Setosa. We've classified out the versicolor from the Virginia. We can get pretty good with we've done perfectly even with just 3. So we don't even need all those. See this confusion matrix? This is how much is classified correctly in each class, and so it's perfectly classified even with just 3. And then let's create a random forest. Kind of the idea of a random forest is that you're sampling from the data without replacement. So what that means is you're creating a bunch of different data sets, and you're building trees on all of them, and then you're having the data sets vote, if you will. And this gives you basically a less overfit data set with a little bit more randomness there. Again, perfectly classified, so let's try to decrease the max depth. And we still get very good. That's partially because random forests, like I said, have significantly less overfitting problems. Though it won't be perfect. It will be perfect even with a max depth of 2. If we had a max depth of 1, though, it would absolutely not be perfect. Remember, you want to have a you want to have, oh, it is perfect with a max depth of 1, but yeah, you want to have a model that is simple, but fits the data both in sample and out of sample well. So now we're going to load a data set that has a little bit more randomness with it in it. This is the California wine data set. For load wine, we're going to create a decision tree classifier. We're going to fit the tree with train, X train, Y train. We're going to predict Y test. And then we're going to create the accuracy, and then we're going to create classification report. So notice we're not fitting everything perfectly. So this is when max depth really changing is kind of something that could be valuable. So if we do max depth equals 2, we can see that it fits the out of sample test data a little bit worse. 4 fits pretty well, and then 3 fits about the same. But eventually, if we have too many trees, we're going to fit the out of sample test data substantially worse. If we have too high max depth, it's going to taper off, and it's going to be a worse model. And then we're going to do random forest. We're going to do a random forest classifier, random forest.fit. Remember, random forest is both for classification and estimation. We get it perfectly. Let's see what happens if we decrease max depth. And the reason why we're able to get it perfectly is because we are able to take into account some of the natural variation in the data set, and then we're able to stop from overfitting as we were in the other one. So we're able to incorporate a more complex model while not necessarily fitting as much directly to the data. And here are the feature importances of each of the features in distinguishing them. So flavonoids was the most important in distinguishing between the wines and then alcohol, and then over here, these are things that are not all that useful. All right, thank you, and I hope you have a great